New Wisdom Unifies Physics. Episode 3. The Atom.
Hello again, I'm your host, Andrew Gray. This episode is about the atom. We will cover the most important experiments about the atom in this episode. We will then add some new wisdom and reveal a new picture of the atom. I'm excited about bringing you this new picture of the atom, the first new picture in about 100 years. I think you'll find this new atomic picture fascinating. But first, a brief history of the atom. It is very helpful to be familiar with atomic history. You must understand the history of atomic physics before you can understand why this new wisdom model makes sense. Okay, history. It was the Greek philosopher Democritus, around 440 BC, who was the first to explain the idea of atoms that make up matter. He argued that you could not divide an object over and over again without limit. Eventually, he argued, you would have to divide down to something so small that it could not be divided anymore. He called this smallest possible division atomos. This ancient Greek word gives us our name for this, the atom. The idea that material things are made up of atoms comes to us from Democritus. However, the atomos viewpoint did not remain popular in the ancient world. In just a few decades, along comes Aristotle. Aristotle just bumps Democritus right out of the way with his viewpoint that everything was made up of earth, fire, water, and air. This was Aristotle's four-element viewpoint. This viewpoint became the accepted theory of matter and remained accepted for over 2,000 years. Just think, the scientific establishment was in a dark age for matter science for over 2,000 years, ignoring the wisdom of Democritus. We really don't want this kind of thing to happen again. But the 2 millennia did pass, and finally, in 1803, the Dark Age ended and the lighted way was shown by British scientist John Dalton. After observing many chemical reactions and how things combine to form new substances, Dalton revived Democritus's atomos. The atomic age was officially restarted. In Dalton's notebook from 1803, we see that he was considering the ultimate particles of bodies for hydrogen, oxygen, azote, carbon, and sulfur. These first 5 ultimate particles of bodies that he believed could not be divided further, Dalton called atoms. After Dalton, many scientists began the study of the elements. Most notably, in 1869, it was the Russian scientist Dmitry Mendeleev who correctly tabulated the periodic nature of the elements and published his periodic table of 60 elements. Mendeleev actually left open spaces for elements he knew had to exist but were not yet discovered. His predictions would all come true and the table would eventually be filled in. However, his table was ordered by atomic weights, except for when the properties of the elements told him otherwise. Mendeleev actually thought the atomic weights of some of the elements were incorrect because he knew they must fit into certain columns in the table because of their chemical properties. This would later be proven incorrect, even though Mendeleev's table was always correct. Another notable discovery of the time was by Robert Bunsen and Gustav Kirchhoff. It was in 1859 that they used a spectroscope and learned that the elements, when heated in Bunsen's burner, gave off characteristic bright lines of just certain resonant frequencies. They were called spectral lines. These spectral lines interested many physicists, and many chemists also participated in the study. Atomic spectroscopy was born. In particular, the spectrum of the simplest element, hydrogen, was of great interest. By 1862, Anders Angstrom had accurately measured the visible spectral lines of hydrogen at 457 terahertz, 617, 691, and 731 terahertz. Then, in 1885, Johann Balmer, a Swiss mathematician, developed a trial-and-error formula for these visible spectral lines of hydrogen. Balmer had wanted a mathematical formula for them, so he just spent time trying different mathematical formulas to see if they would fit. Finally, he came up with his famous empirical trial-and-error Balmer formula for the visible spectrum of hydrogen. Rearranged, it looks like this. The visible frequencies of hydrogen is equal to some constant times 1 over 2 squared minus 1 over n squared, where n equals 3, 4, 5, 6, and so on, and where c is a constant matched to the experimental data. This trial and error formula was highly accurate, and it fascinated another scientist, Sweden's Johannes Rydberg. Rydberg was working on another empirical formula of his own. By 1887, while studying the spectral series of the alkali metals, Rydberg noticed that the spectra usually were in multiple groups in several series of lines and not just one group. So he surmised an extension to Balmer's formula. This was his famous empirical formula, the Rydberg formula. All the frequencies of hydrogen equals some constant times 1 over m squared minus 1 over n squared, where m and n equal 1, 2, 3, 4, 5, 6, and so on, with n greater than m. And again, c is a constant matched to the experimental data. From this logical formula, Rydberg had predicted all of the hydrogen spectral series, only one of which had been seen experimentally. Both the Balmer and Rydberg formulas were trial and error empirical formulas, and both were simply matched to the experiment. They just tried this and tried that until they came up with these formulas. But both formulas for the hydrogen spectra were highly accurate. And don't forget, Rydberg had amazingly predicted all the other hydrogen series before they were even seen experimentally. But let us emphasize here that Rydberg's predictions were made from trial and error formulas and were simply matched to the experimental data. In 1897, just a decade after Rydberg's work, J.J. Thomson was able to prove the indivisible idea of both Dalton and Democritus wrong by proving that the atom was divisible. He proved it was divisible by discovering one of its parts, the electron. Thomson discovered the electron in 1897. In 1897. It is amazing to us to realize that Rydberg formulated his hydrogen spectrum before the electron was even discovered. This is an amazing revelation. Think about that. Rydberg knew the frequencies for all the hydrogen emissions before it was even known that the electrons were doing the emitting. Anyway, Thomson's discovery of the electron proved that the atom has parts and was not indivisible as Dalton and Democritus claimed. In particular, he proved that the atom has negative charges in it. And since atoms are neutral, then they must also have positive charges in them. Thomson suggested a model for the atom which he likened to plum pudding. In Thomson's plum pudding model, Thomson thought that the negatively charged electrons were like the plums floating around in the positively charged pudding. The electrons would be distributed evenly throughout the plum pudding atom. This suggestion would soon be tested. It was Hans Geiger and Ernest Marsden, while working in Ernest Rutherford's lab in 1909, who would test the plum pudding model for the atom in a scattering experiment. Here is their experimental setup. They used a radioactive source that emitted energetic alpha particles. With these alpha particles, they were going to probe a micro-thin foil of gold. Were the gold atoms in the foil plum pudding style atoms? That is what they wanted to find out. So they shot positively charged alpha particles at the gold foil. From Thomson's plum pudding model, with the positive charge unconcentrated like the pudding, so to speak, they expected all the heavy alpha particles to shoot right through the super thin gold foil unimpeded, like this. But that is not what happened. Most of the alpha particles did go straight through, but some of the alpha particles were observed being ejected backwards back out of the gold foil, like this one, and this one, and this one. How could this be? Most went right through, but some were deflected backwards. Rutherford said, "It was like firing a cannon shell at a piece of tissue paper and seeing it bounce right back at you." It was difficult for Rutherford to believe these results. Rutherford would have to ponder over them for a while. Rutherford realized that the plum pudding model for the atom had to be wrong, but what in the heck was it? After quite a bit of contemplation, Rutherford finally realized that in order for the heavy alpha particles to be knocked totally backwards, the positive charge in the gold atoms must be concentrated into a tiny central region of the atom. The diffuse plum pudding style distribution of positive charge just could not do this. The plum pudding model was gone. Concentrated positive charge in the central region was required to deflect the alpha particles like Geiger and Marsden had seen in their experiment. Rutherford named this positively charged central core the nucleus. Nucleus comes from the Latin word for kernel, like the kernel of a nut. Rutherford surmised that this extremely tiny, positively charged nucleus was what was responsible for deflecting the charged alpha particles backwards. He then formulated the scattering of the alpha particles going through the gold foil very successfully. The Rutherford model was indeed successful, and in a very surprising way. Number 1. The atom must consist of negatively charged electrons whirling around a tiny little positively charged nucleus which is concentrated at the center of the atom. Number 2. This means that the atom must be mostly empty space. And this means that matter itself must be mostly empty space. How surprising to find out that matter is made up of mostly empty space. And number 3, Rutherford also was able to deduce the approximate value of the nuclear charge. the nuclear charge is approximately equal to half the atomic weight multiplied by the electronic charge. So amazingly, Ernest Rutherford had gotten a pretty good picture of the atom with his model by 1911. First, he figured out that the mass of the concentrated nucleus is approximately 1/2 positively charged matter and 1/2 neutral matter. And second, electrons with little mass are whirling around the nucleus. This second observation would cause turmoil in physics for over a century, as physicists have attempted to explain how electrons can whirl around without radiating. We will talk about atomic electron accelerations in great detail later in this video. It was still 1911 when Antonius van den Broek, a Dutch physicist, proposed that it was the number of protons that gave the order of each element in the periodic table and not the atomic weights. 2 years later, in 1913, this was confirmed. A young English physicist named Henry Moseley was plotting certain X-ray resonant frequencies for each successive element. That is, when an element is bombarded with electrons, it gives off a resonant X-ray frequency unique to that element. So, for example, one set of X-ray resonant frequencies that Moseley plotted is seen here in the graphic. Z is the number of protons in each nucleus, now called its atomic number. Its atomic number Z. And F sub X-ray is the resonant X-ray frequency for that element. He found that as Z minus 1 squared of each element went up, then its X-ray resonant frequency went up as well, and in a linear fashion. This relationship is now called Moseley's law. Moseley was ingenious in finding this relationship for the elements. And when Moseley arranged the elements of the periodic table by their atomic number instead of their atomic weights, the flaws in the ordering of the periodic table just disappeared. Now chemists could rest assured that the atomic numbers were what ordered the elements in the periodic table, and not their atomic weights. It was Moseley's X-ray studies that made this possible. It was just 5 years later, in 1918, that Rutherford was at it again. He was shooting alpha particles into nitrogen gas and recognized hydrogen nuclei emerging from the gas. What Rutherford was doing was performing the first nuclear reaction where it was understood what was actually going on. He understood that a nuclear transformation was occurring. That is, an alpha particle is bombarded into a nitrogen nucleus, and that's converted into an oxygen nucleus plus P, a hydrogen nucleus. Rutherford knew that hydrogen was the lightest element in the periodic table. His discovery that the hydrogen nucleus could be knocked out of other nuclei like nitrogen led him to realize that this was the positively charged fundamental building block of the nucleus that he had discovered. So, he needed to name it. He considered the name protyle, proton after physicist William Prout, and proton, the Greek word for first. The consensus that emerged was the name proton. Rutherford gave us the name proton in 1918. And Rutherford was not yet finished. In 1920, Rutherford speculated on the possible existence of the neutron in the nucleus during one of his lectures in London. And just a dozen years later, one of his grad students, James Chadwick, actually discovered the neutron by bombarding beryllium with alpha particles. As seen in the diagram, an alpha particle bombards a beryllium nucleus and produces a carbon nucleus plus a neutron. Chadwick could not directly detect these neutrons due to their neutral charge. So he allowed these neutrons to blast into some paraffin so that some secondary protons would be knocked out. Using a clever billiard ball type calculation for this collision, Chadwick was able to determine that the neutrons were slightly more massive than protons and neutral in charge. We have the name neutron from 1932 from James Chadwick. So after Chadwick's discovery of the neutron in the nucleus, the physics world had a fairly good experimental picture of the atom. Chadwick and Rutherford's planetary atomic model was a fairly good picture by the 1930s. Positive protons and neutral neutrons bound together in the nucleus of the atom, with negative electrons whirling around this nucleus. But there was one big problem with Rutherford's planetary model. What was this big problem? Well, electrons radiate when accelerated. Electrons radiate electromagnetic radiation when accelerated. So if negatively charged electrons were whirling around the nucleus, then they would be centripetally accelerated, and this would cause constant electromagnetic radiation. But we just don't see this constant radiation. Atoms do not constantly radiate. So this was a big problem with Rutherford's planetary model, and indeed, physicists in the early 1900s abandoned it. You must understand this big radiation problem with the planetary atomic model to understand why physicists in the early 1900s abandoned the planetary model. And this will be key to understanding the new wisdom picture of the atom. You must understand why static electrons that are being centripetally accelerated around a nucleus would constantly radiate. Once you understand this, you will be able to understand why physicists abandoned Rutherford's planetary atomic model. Okay, so first let's review accelerated electrons and their radiation. Then we will explain the Rutherford problem. Isaac, are you still there?
Yes, Andrew. Of course, I'm still here.
Isaac, do you remember the scene from episode 1 where we talked about accelerated electrons and their radiation?
Yes, Andrew. I do remember it.
Okay then, Isaac. Let that scene roll, and let it roll twice. Or, if you had medium-fast accelerations of the electrons, these would generate medium-fast X-rays. Or, if you had medium-fast accelerations of the electrons, these would generate medium-fast X-rays. In this clip, we saw that when a static charge is accelerated, it gives off electromagnetic radiation. While not accelerated, even with constant velocity, it doesn't. And in this case, the acceleration is linear, not centripetal. Linear in the same direction as the velocity. So the point is that whenever a static charge is accelerated, it will emit electromagnetic radiation. Charge acceleration implies electromagnetic radiation. So we need to investigate what happens with centripetal accelerations. Centripetal acceleration is perpendicular to the velocity and not linear in the same direction as the velocity. So let's look at a simple case first. Just one acceleration perpendicular to the velocity. Isaac, roll that left turn footage. Here we see an acceleration of the charge where the acceleration is not in the same direction as the velocity of the charge. The charge still radiates. When the charge gets to the left turn, it sends out a transverse radiation pulse. We will pause the action to see that the charge does not radiate along the direction of the acceleration. Isaac, pause the action now. We see the transverse radiation rippling out between the radial electric force lines. But notice the electric force lines parallel to the acceleration, shown here blinking in red. There is no transverse pulse along these lines. So in general, if the velocity is not too high, then most of the electromagnetic radiation is emitted perpendicular to the acceleration of the charge. Keep this in mind. Most of the electromagnetic radiation goes out perpendicular to the charge's acceleration. Isaac, let the action roll again so we can watch. Okay, next we want to combine 4 left turns so we can have an orbit. Here is our test 4-corner orbit. Each time the electron is accelerated and turns at one of the 4 corners, it will emit electromagnetic radiation. While the electron is on the straight side, it's not accelerated, so it won't emit radiation there. Isaac, roll the 4-corner orbit footage. You can see that our test electron emits electromagnetic radiation each corner with each acceleration. Not only that, an observer in the distance would perceive these pulses as electromagnetic waves coming at him with the same frequency as the orbital frequency of the electron. That is, this test electron going around like this would generate an electromagnetic wave at a distance with the same frequency as the orbital frequency of the electron. I think you get the picture here. Now we want to increase the number of corners of the orbit more and more. Eventually, as the number of corners is increased enough, we will simulate acceleration that is constant for a circular orbit. Remember, this is our goal, to understand how a circular orbit would generate electromagnetic waves. So first we increase the number of corners to 6. Here is our 6-sided test orbit. This time the test electron will be accelerated at the 6 corners and emit electromagnetic radiation there. Isaac, roll the 6-sided test orbit, please. Again, we see the electron only emits electromagnetic radiation when it's accelerated. It does not emit when it's not accelerated. And again, these periodic accelerations would generate electromagnetic waves at a distance that an observer would perceive to have the same frequency as the electron's orbital frequency. Okay, now we increase the number of corners to 8. Here is an 8-sided test orbit. Just imagine what would happen in this orbit. It would be very similar. We will leave this simulation to your imagination. And now, here is a 12-sided orbit. Just imagine what would happen here. The accelerations would be more and more numerous and less intense. The accelerations would tend to run together. We will also leave this simulation to your imagination. But you see that we're getting closer and closer to acceleration all the time as we increase the number of corners. And indeed, this is just what we're after. We want you to understand what is happening when an electron in a circular orbit radiates electromagnetic energy. So imagine we have increased the number of corners to infinity, and we arrive at our circular orbit. Here is our circular test orbit. Isaac, zoom out and roll the circular footage, please. Finally, we can see and understand how a test electron would radiate if put into a circular orbit. Notice that since the centripetal acceleration is constant, then the test electron is emitting electromagnetic radiation all the time. The test electron in this so-called planetary orbit is constantly emitting electromagnetic radiation. That is, the test electron is being accelerated all the time, so it's radiating all the time. Finally, we can see why and how an electron moving in a circular planetary orbit would radiate all the time. So this is why physicists in the early 1900s abandoned Rutherford's planetary model, because atoms do not radiate all the time. Generally, they do not radiate. Atoms in a cool vapor just do not radiate at all. So indeed, atoms do not consist of statically charged electrons going around the nucleus. This is because they would always radiate, and they do not. This is not the picture for the atom. The electron with a static negative charge orbiting around the nucleus in a circular planetary orbit is gone, impossible, rejected. This is obviously not what is happening. This may surprise some of you viewers, especially you electrical engineers who really have not paid attention over the years. When I ask an electrical engineer why electrons do not radiate while being accelerated in atoms, they say, "Huh?" But a statically charged electron in a planetary orbit is just impossible. Atoms do not have statically charged electrons moving in orbits. You electrical engineers, think about this. If you have a circular omnidirectional antenna, it radiates, so why don't the electrons in orbits around the nucleus radiate? We will answer this question, but first, we continue with our history now that we know why physicists abandoned the planetary model in the early 1900s. Theorists were faced with the fact that an electron with a static charge could not be orbiting the nucleus. The theoretical challenge was, and still is, very daunting. So now we can continue with our history, now that we know why physicists abandoned the planetary model in the early 1900s. Theorists were faced with the fact that the electron with a static charge could not be orbiting the nucleus. The theoretical challenge was, and still is, very daunting. So the first notable gentleman to step up and try a new atomic theory was Niels Bohr. In 1913, Bohr not only had to deal with the electron orbit radiation problem, but Bohr had to explain the Rydberg hydrogen frequencies given off by hydrogen. Remember Rydberg? Rydberg had found the empirical formula for the hydrogen frequencies way back in 1887, and these were still unexplained. So Bohr thought, if he could somehow make the electron orbits have energy levels proportional to 1 over n squared, then the energy difference between two levels m and n would be proportional to 1 over m squared minus 1 over n squared. Then, Bohr thought, he could match Rydberg's hydrogen spectrum if he used Einstein's light particles. These light particles would be given off during a transition between energy levels in his theory. And that is exactly what he did. And it was a noble effort. But Bohr's theory did have flaws. Its major flaw was that the electrons still traveled in circular orbits, yet Bohr could not explain why the electrons did not radiate. Bohr simply proclaimed the electrons' radiation away. Bohr simply stated that the electrons did not radiate in these special orbits. The special orbits were special, according to Bohr, because they did not radiate. Bohr's theory had to be abandoned. The next notable gentleman to step up and offer an atomic theory was Erwin Schrödinger. In 1926, Erwin Schrödinger postulated a differential equation, the Schrödinger wave equation. His equation was a so-called matter wave equation for the electron based on the ideas of de Broglie, and it had energy solutions that mimicked the energy level behavior of Bohr's theory. But in Schrödinger's theory, the electron is described as a matter wave and does not have any definite orbits. In Schrödinger's theory, one cannot know the reality of the electron situation, only probabilities of detections. Reality had been expressly excluded. In fact, Schrödinger, along with Werner Heisenberg, claimed that the reality of the electron situation cannot be known. In 1927, Heisenberg proposed an uncertainty principle describing this situation. Basically, if you are theoretically going to convert a particle electron into a wave electron, you have smeared out any possibility for a definite electron orbit. What you are left with are probability plots, like seen in the graphic, and energy levels similar to the ones of Niels Bohr. So that is basically where we are today in the history of the atom. The Schrödinger-Heisenberg picture of the atom is still the accepted theory of today. However, this picture is not without its flaws. And the major flaw of this theory is its claim that no picture of reality exists at the microscopic level. Any theory with no picture of reality is a theory barking, barking up the wrong tree.
Barking up the wrong tree means that somebody makes a wrong choice, or directs his or her efforts in the wrong direction.
Indeed, the Bohr and Schrödinger theories went in the wrong direction. They did not know about the pulsating nature of charges back almost 100 years ago, and they gave up on a planetary model for the atom way too soon. Look, it's simple. If the electron pulsates off while it's being accelerated, then the electron won't radiate. So now, Isaac, sound the trumpets. New wisdom is here to get us back to non-radiating planetary orbits. This is coming right up in the Atom Part 2.